Welcome to the PWM video. In this here video, I'll obviously briefly go over the ideas of PWM. So just to start off, for those of you who aren't familiar with the acronym PWM, PWM stands for pulse width modulation. Essentially, we're changing the width of a pulse or the shape of a wave, which represents the state of our output. This allows us to mimic the effects of an analog signal to control things like the brightness of an LED, the volume of the speakers, things like that. So to demonstrate, I'm going to draw a square wave. And simply enough, when the wave is high, the output is on. When the wave is low, the output is off. With this, there are a couple of important terms that we need to define in order to describe our PWM. These are pulse width, duty cycle, and period. Pulse width and duty cycle are pretty closely related, but we'll get into that in a minute. First we need a period, which is similar to a period for a sine wave, and for that I'll draw some dashed lines. So the period is just our constant length of time in which we'll vary the pulse width to adjust our effective power as a percentage of the total period. And I believe there may be a couple of variations of PWM, but in this simple example, we'll have the signal start on at the beginning of each period, switch off at some point in the middle, and then back on at the beginning of the next period. In this first example, I've drawn a 50% duty cycle. As you can see, for a 50% duty cycle, the output is on for half the time of the period and off for the remaining half. As you should hopefully see, this makes our pulse width 1/2 the period. Now, by changing the point where the output goes low, we're modulating the width of the pulse to change the duty cycle, and thus the effective power output. Note that the pulse width doesn't have to be the same for every period, but it will likely be the same for at least a few, just because of how fast the output will be switching on and off. Just to give you a quick idea of scale, a small microcontroller like the TI MSP430 D2553 can run with a clock speed of 16 megahertz, which is also known as 16 million clock cycles a second. And so here, for another example, I'll draw a 20 or 25% duty cycle. Our output will be on for about 20% of the time and off for about 80%. If we were to have this output connected to a light, like an LED, this would give us a 20% brightness. So when I first learned about PWM, I was a little confused how it was different from something like a sine wave, which also has a period. Why can't we just change the frequency, turn things on and off faster and slower? The problem with this is you still end up with the same amount of time spent on as you do off. Just to visualize this really quick, here we have two sine waves and some period lines. You'll notice that within each period you have the same amount of time above the line as well as below it. Hopefully from this you can see why this doesn't work for PWM. Basically we need to be able to vary the midpoint within each period where the wave crosses the x-axis, which you can't do with your standard sine wave. And with that, I shall sign off. Anyway, thanks for watching. I hope this was helpful, but in the event that it was not, please make sure to ask about it in class.